Something beneath Indonesia is changing again. Not because a single dramatic explosion has already happened, but because one of the most closely watched volcanic systems on Earth has begun producing the same kinds of signals that have forced scientists to pay attention before. Ash continues to rise above Anak Krakatau. Shallow earthquakes are repeatedly shaking the volcanic edifice, and every new observation is being measured against the memory of one disaster that claimed more than 36,000 lives in just a matter of hours. The question isn't whether history repeats itself exactly, it's whether the same geological machine is beginning to move once more. If you follow volcanic hazards, you already know why that possibility matters. Subscribe if you appreciate careful, evidence-based disaster analysis, because this is a story that is still unfolding. And to understand where it may be heading, we first have to go back to where it all began, to understand why scientists never take renewed activity at Anak Krakatau lightly. You have to go back to one of the most devastating volcanic disasters ever recorded. Nearly every discussion about this volcano begins with the eruption of Krakatoa in 1883, and for good reason. That event didn't simply destroy an island. It permanently changed the geography of the Sunda Strait, altered the atmosphere around the world, generated catastrophic tsunamis, and killed more than 36,000 people in only a few hours. More importantly, it created the very volcanic system that continues to evolve today. Anak Krakatau is not a separate volcano with an unrelated history. It is the direct continuation of that disaster. The volcano that concerns scientists today exists because of what happened nearly a century and a half ago. Before 1883, Krakatoa was a volcanic island sitting between the Indonesian islands of Java and Sumatra inside the Sunda Strait. This narrow stretch of water has always been one of the busiest maritime corridors in Southeast Asia, linking the Java Sea with the Indian Ocean. Beneath those waters lies one of the most active tectonic boundaries on Earth. The Indo-Australian plate slowly pushes beneath the Eurasian plate in a process known as subduction. Every year, that movement forces enormous amounts of oceanic crust downward into Earth's mantle. As the descending slab heats up, water trapped inside the rock is released into the overlying mantle, lowering its melting point and producing magma. That magma has only one long-term destination. It wants to rise. Indonesia sits directly above this gigantic geological engine. Stretching thousands of kilometers across the archipelago is the volcanic chain known as the Sunda Arc, home to well over 100 active volcanoes. Many erupt quietly for years before settling down again. Others remain silent for decades before producing sudden explosive activity. A handful are capable of changing history itself. Krakatoa belongs in that final category. The eruption of August 1883 was not one single explosion, but a sequence of escalating events that culminated in several enormous blasts. Contemporary observations, combined with modern geological research, suggest that huge volumes of gas-rich magma rapidly fragmented beneath the volcano, releasing energy on a scale almost impossible to imagine. Entire sections of the volcanic island collapsed into the partially emptied magma chamber below. That collapse displaced tremendous volumes of seawater, generating massive tsunamis that raced across nearby coastlines. Those waves became the deadliest part of the catastrophe. Entire coastal villages disappeared, ports were erased, ships weighing thousands of tons were carried inland as though they were toys. In many places, people never saw the waves coming. Communication in the 19th century was slow, warning systems barely existed, and the concept of tsunami preparedness was still poorly understood. Within only a few hours, tens of thousands of people had lost their lives. The eruption itself was extraordinary for another reason. It was heard thousands of kilometers away, making it one of the loudest sounds ever documented in recorded history. Atmospheric pressure waves circled the globe multiple times. Ash and sulfur-rich aerosols reached high into the atmosphere, scattering sunlight and producing spectacular sunsets, observed around the world for months afterward. Global temperatures temporarily cooled as volcanic particles reflected part of the sun's energy back into space. Even today, volcanologists continue studying the 1883 eruption because it remains one of the defining examples of how interconnected Earth systems really are. A volcano located between two Indonesian islands briefly influenced weather, climate, shipping, communications, and human history on an international scale. But the story didn't end when the explosion stopped. After the collapse, much of the original volcanic structure disappeared beneath the sea. For decades, the caldera left behind appeared relatively quiet. To someone looking across the Sunda Strait at the beginning of the 20th century, it might have seemed that Krakatoa had simply vanished forever. Nature had other plans. Deep beneath the flooded caldera, magma was still accumulating. The subduction zone had not stopped operating. The tectonic plates had not paused. The enormous geological conveyor belt continued exactly as it had before the catastrophe. Pressure slowly rebuilt beneath the seabed. Then, in 1927, fishermen and local observers began reporting something remarkable. Steam started rising from the ocean. Shortly afterward, repeated underwater eruptions pushed volcanic material toward the surface. Lava, ash, and fragmented rock accumulated faster than waves could wash them away. Bit by bit, a new island began emerging from the sea. It was eventually named Anak Krakatau. The name translates simply to Child of Krakatoa. It is one of the most appropriate names ever given to a volcano, because that is precisely what it is. Anak Krakatau is not merely located near Krakatoa. It was born directly from the magma system left behind by the 1883 collapse. It inherited the same tectonic setting, the same magma supply, and many of the same hazards that made its parent volcano infamous. Since its birth, Anak Krakatau has grown through repeated eruptions. Layers of lava flows, volcanic ash, bombs, and loose pyroclastic deposits gradually built a steep volcanic cone, rising hundreds of meters above sea level. Unlike ancient volcanoes that have had thousands of years to stabilize, Anak Krakatau is geologically young. Every eruption adds new material, but much of that material remains loose, fractured, and structurally weak. That detail matters more than many people realize. A volcano is not simply a mountain with a crater on top. It is an evolving structure whose stability depends on how it grows, how magma moves inside it, how gases escape, and how gravity constantly pulls on every layer deposited during previous eruptions. When new lava accumulates unevenly, or when explosions weaken one side more than another, the entire volcanic cone can become unstable. Imagine continuously stacking wet sand onto one side of a steep pile, while vibrations shake it from underneath. At some point, gravity wins. Volcanologists have spent years studying exactly how these growing volcanic islands evolve, because collapses can sometimes become as dangerous as eruptions themselves. A collapse doesn't require the most explosive eruption imaginable. Sometimes it only requires enough weakening at precisely the wrong location. This is why monitoring Anak Krakatau involves far more than simply watching for ash clouds. Scientists examined seismic activity, gas emissions, thermal imagery, satellite deformation measurements, crater changes, slope stability, and shoreline evolution. Every dataset provides another clue about what is happening beneath the surface. Most days, these observations show the normal behavior expected from one of Indonesia's persistently active volcanoes. Small eruptions occur, ash columns rise and dissipate. Lava occasionally reaches the surface. Seismic instruments record constant volcanic movement. None of those observations automatically mean catastrophe is imminent. But history has taught researchers something extremely important. This volcano has already demonstrated that relatively modest eruptive activity can still produce devastating secondary hazards if the structure itself becomes unstable. That lesson fundamentally changed how scientists view Anak Krakatau. It shifted attention away from asking only one question: will it erupt? Toward a much broader one: what is the volcano actually building toward? Because the greatest danger may not come from the eruption people can see. It may come from the part of the volcano they cannot see at all. And that is exactly where today's renewed activity begins to raise difficult questions. The ash is only the visible symptom. The real story lies much deeper underground, where instruments are now detecting changes that scientists cannot afford to ignore. The most important question surrounding Anak Krakatau today is not whether it is erupting. It is. The question is whether the pattern of activity now being recorded represents the normal rhythm of one of the world's most active volcanoes, or whether it is the early stage of something larger developing beneath the surface. That distinction is everything. Volcanoes rarely move from complete silence to catastrophic eruption without leaving clues. They communicate continuously. The challenge is that they do not communicate in plain language. They speak through earthquakes too small for people to feel. Changes in gas chemistry invisible to the human eye. Subtle swelling of the ground measured only by satellites, and ash emissions that can either represent routine pressure release or the first visible sign of increasing unrest. Every one of those signals has to be interpreted together. As of early July 2026, Indonesia's volcanic monitoring agencies continue to keep Anak Krakatau under close observation as it produces recurring eruptive activity and intermittent ash emissions. Like many volcanoes in the Sunda Arc, the volcano has experienced periods of elevated activity before. On their own, ash plumes are not unusual. Anak Krakatau has generated numerous explosive bursts throughout its short lifetime. But experienced volcanologists never focus on only one observation. Instead, they ask whether multiple independent indicators are beginning to tell the same story. Imagine visiting a doctor. A slight fever by itself may not mean much. Neither might an elevated heart rate. A cough alone could have dozens of explanations. But when several symptoms begin appearing together, doctors become far more interested in identifying the underlying cause rather than treating each symptom individually. Volcano monitoring works in much the same way. One ash plume rarely causes alarm. One shallow earthquake may not either. A brief increase in volcanic tremor can occur naturally. But if ash emissions increase while shallow earthquakes become more frequent, volcanic tremor persists, gas output changes, and thermal observations indicate fresh magma approaching the surface, scientists begin asking a different question entirely. Are all of these observations connected? That is why every new report from Anak Krakatau is evaluated as one piece of a much larger puzzle. Among the most closely watched indicators are volcanic earthquakes occurring at relatively shallow depths beneath the cone. These events differ from the tectonic earthquakes that Indonesia experiences along major fault systems. Tectonic earthquakes occur because enormous sections of Earth's crust suddenly slip against one another. Volcanic earthquakes are different. They're often produced when magma forces open fractures inside the rock, when gases rapidly expand under pressure, or when fluids circulate through newly formed cracks. Each small earthquake represents stress being redistributed beneath the volcano. One earthquake proves very little. A sustained sequence may indicate magma is actively moving. Scientists also monitor what is known as volcanic tremor. Unlike individual earthquakes, tremor resembles continuous vibration. Instead of isolated seismic spikes, instruments detect an ongoing signal lasting minutes, hours, or even longer. You can think of earthquakes as individual knocks on a door. Tremor is more like hearing machinery continuously running behind the wall. Persistent volcanic tremor often suggests fluids, gas, or magma remain in motion beneath the volcano. It does not automatically predict a major eruption, but it tells scientists that the volcanic plumbing system is active, and that plumbing system is extraordinarily complex. Beneath Anak Krakatau lies a network of conduits, fractures, magma reservoirs, and gas pathways that constantly evolve as eruptions reshape the volcano. Some pathways seal shut while others open unexpectedly. Pressure builds in one location before escaping through another. Every eruption slightly changes the architecture hidden beneath the island. That means the volcano itself is never exactly the same from one year to the next. Another critical observation involves volcanic gases. Long before magma actually reaches the surface, gases dissolved within it begin escaping. Water vapor remains the dominant volcanic gas, but scientists pay especially close attention to sulfur dioxide and carbon dioxide, because changes in their release rates can reveal what magma is doing below ground. Picture a bottle of carbonated soda. As long as the cap remains sealed, much of the gas stays dissolved within the liquid. Once pressure decreases, bubbles rapidly begin escaping. Magma behaves similarly. As magma rises toward lower pressure near Earth's surface, dissolved gases separate and expand. Measuring those gases allows volcanologists to estimate whether fresh magma may be ascending through the system. Satellites now play an equally important role. Space-based instruments continuously monitor volcanic heat, sulfur dioxide emissions, ash dispersion, and even tiny changes in ground elevation. Some radar satellites can detect deformation measuring only a few centimeters across large volcanic regions. Why does that matter? Because volcanoes frequently swell before eruptions. As magma accumulates underground, it pushes surrounding rock outward. The movement may be completely invisible to people standing nearby, yet satellites hundreds of kilometers above Earth can measure it with remarkable precision. If deformation accelerates while seismicity increases and gas emissions change, confidence grows that magma itself is responsible. Again, no single observation tells the full story. Scientists rely on convergence. Several independent datasets pointing toward the same conclusion provide far stronger evidence than any one measurement alone. Visual observations remain important too. Ash plume height, eruption frequency, crater morphology, incandescent material during nighttime observations, and lava emplacement all help volcanologists understand how efficiently the volcano is releasing pressure. Ironically, a volcano that erupts frequently can sometimes reduce the likelihood of larger explosive events by allowing pressure to escape gradually. Other times, repeated small eruptions simply represent pressure leaking from one part of the system, while much larger volumes continue accumulating below. Distinguishing between those possibilities is one of the greatest challenges in modern volcanology, and there is another complication. Volcanoes often behave differently despite appearing similar. Researchers have documented volcanoes producing weeks of intense seismic unrest before relatively modest eruptions. Others remain comparatively quiet before generating unexpectedly violent explosions. Some deform significantly, others barely deform at all. Some release enormous amounts of sulfur dioxide before erupting. Others trap gases until explosive fragmentation suddenly occurs. Nature refuses to follow a single rulebook. That uncertainty explains why volcanic alert levels are based on observed hazards rather than absolute predictions. Monitoring agencies evaluate the current evidence, assess the likelihood of different scenarios, establish exclusion zones where necessary, and continuously update guidance as new information becomes available. The goal is not to predict the exact hour of an eruption months in advance. No scientist can do that reliably. The goal is to recognize meaningful changes early enough that emergency managers and nearby communities have time to respond if conditions continue deteriorating. For people living around the Sunda Strait, those updates matter enormously. Fishing communities, ferry operators, commercial shipping, tourism businesses, aviation authorities, and disaster management agencies all depend on accurate monitoring. Even relatively small ash eruptions can disrupt aircraft routes. Falling ash affects machinery, water supplies, agriculture, and visibility. Larger explosive episodes introduce additional hazards, including ballistic rocks, pyroclastic density currents near the volcano, and, under certain conditions, tsunami risk. That last hazard remains the one scientists never ignore. Because Anak Krakatau occupies a unique position, it is not simply an active volcano, it is an active volcano rising directly from the sea. Every eruption changes the shape of the island itself. Lava builds new slopes. Explosions remove old ones. Loose volcanic deposits accumulate at steep angles where gravity is constantly working against stability. The volcano is literally constructing the landscape that may determine its own future behavior. And that leads directly to the question researchers continue asking every time new activity is recorded. What is happening inside the mountain is important. But what is happening to the mountain itself may ultimately prove even more critical. Because beneath the ash clouds and seismic graphs lies another threat, one capable of transforming an ordinary eruption into an ocean-wide emergency within minutes. If there is one lesson volcanologists have learned from studying Anak Krakatau, it is that the most dangerous part of a volcano is often the part nobody can see. Every photograph captures the summit, every news report focuses on the ash cloud, every drone video follows glowing lava spilling down the slopes. But none of those images reveal where the real decisions are being made. Those decisions happen several kilometers beneath the surface, inside a constantly evolving plumbing system where magma, dissolved gases, fractured rock, and immense pressure interact every second of every day. That hidden world determines whether an eruption quietly releases pressure, builds toward a much larger explosion, or destabilizes the volcano itself. To understand why today's activity is receiving so much attention, you first have to understand how volcanic pressure actually works. Contrary to what many people imagine, magma does not rise because it is being forced upward like toothpaste squeezed from a tube. The process is much more dynamic. Magma is generally less dense than the solid rock surrounding it, so it naturally tends to rise through weaknesses in Earth's crust. As it ascends, however, something equally important begins to happen. The pressure around the magma decreases, and that changes everything. Deep underground, the enormous weight of overlying rock keeps volcanic gases compressed within the molten material. Water vapor, carbon dioxide, sulfur dioxide, and other gases remain dissolved inside the magma, much like carbon dioxide remains dissolved inside a sealed bottle of sparkling water. But the higher the magma rises, the less pressure exists above it. As pressure drops, those gases begin separating from the liquid magma, forming expanding bubbles. Now imagine billions upon billions of bubbles forming inside an already pressurized volcanic system. Those bubbles occupy far more volume than the dissolved gases they came from. As they expand, they increase internal pressure, fracture surrounding rock, and can accelerate the upward movement of magma itself. In many explosive eruptions, it is not the molten rock alone that creates the violence, it is the rapid expansion of volcanic gas. That is why volcanologists often say gas drives the eruption. The magma supplies the material, the gases supply much of the explosive energy. This process also explains why scientists devote so much effort to monitoring sulfur dioxide emissions. A noticeable increase in gas output can suggest that fresh magma is approaching shallower levels. Conversely, a sudden decrease is not always good news. Sometimes reduced gas emissions simply mean escape pathways have become blocked. Think of placing your thumb over the end of a garden hose. The water has not stopped flowing, the pressure has increased. A blocked volcanic conduit can create similar conditions. If gases cannot escape efficiently, pressure may continue building until the system eventually fails in a much more energetic way. That is one reason why interpreting volcanic gas data requires so much caution. High emissions can indicate active degassing. Low emissions can mean declining activity, or a sealed system storing energy beneath the surface. Context matters. Pressure alone is only one piece of the story. Another equally important concept is magma viscosity. Not all magma behaves the same way. Some magma is relatively fluid, allowing gases to escape more easily. Other magma is much thicker and stickier, trapping gases as pressure steadily rises. You can think of the difference between pouring water and squeezing thick honey from a container. Water flows almost immediately. Honey resists movement. Gas bubbles also escape far more easily through water than through honey. Although Anak Krakatau often produces magma capable of relatively frequent eruptive activity, its behaviour can still change significantly, depending on the composition of newly arriving magma, the amount of dissolved gas it contains, and how efficiently the volcanic conduit remains open. This is why every eruption is different. The volcano is never operating under exactly the same internal conditions twice. Scientists also pay close attention to harmonic tremor, one of the more fascinating signals produced by active volcanoes. Earlier we discussed volcanic tremor as continuous vibration rather than individual earthquakes. But harmonic tremor deserves a closer look because it often tells researchers that fluids are actively moving through the volcanic plumbing system. Imagine blowing steadily across the opening of a bottle. The air inside resonates, producing a continuous tone. Something similar can occur inside volcanic conduits as magma and gases move through narrow passages. Instead of hearing sound, seismometers detect continuous vibrations generated by that movement. The important point is not that harmonic tremor automatically predicts a major eruption. It doesn't. The important point is that it confirms the volcanic engine is actively operating beneath the surface. And when harmonic tremor appears alongside shallow earthquakes, ongoing degassing and recurring eruptive activity, scientists naturally begin examining whether all those observations share the same underlying cause. Then there is deformation. One of the remarkable advances in modern volcanology is the ability to measure changes in the shape of an entire volcano with extraordinary precision. Instruments placed on the ground and satellites orbiting hundreds of kilometers above Earth can detect whether parts of the volcano are slowly rising, sinking, expanding, or tilting. Why would a volcano change shape? Because rock bends. It may not seem that way when you stand on a mountain, but under sufficient pressure, Earth's crust behaves more like a flexible material than an unbreakable solid. As magma accumulates underground, it pushes surrounding rock outward. The surface may lift only a few centimeters, but those small movements reveal enormous forces acting below. Think of inflating a balloon beneath a thick blanket. The blanket rises even though you cannot directly see the balloon. Volcanoes deform for the same basic reason. Scientists compare successive measurements over days, weeks, and months, looking for acceleration, stabilization, or reversal. Rapid inflation combined with increasing seismic activity often attracts significant attention, because both observations may indicate additional magma entering the system. But deformation can also stop. Sometimes the volcano finds a new equilibrium. Sometimes magma cools before reaching the surface. Sometimes pressure is released through smaller eruptions instead of larger ones. Again, there is no single formula. Volcanology remains a science of probabilities rather than certainties. That uncertainty frustrates many people outside the scientific community. Headlines often ask a simple question: will the volcano erupt? Scientists rarely answer that question directly because it is the wrong question. The better question is, how is the probability of different hazardous scenarios changing? Notice the difference. Forecasting volcanic hazards resembles forecasting severe weather far more than predicting the result of a scheduled event. Meteorologists cannot promise that every supercell will produce a tornado. Instead, they evaluate the environment, identify the ingredients, estimate probabilities, and issue warnings when risk increases. Volcanologists operate in much the same way. They assess magma movement, gas release, seismicity, deformation, thermal anomalies, visual observations. Then they combine every dataset into the most accurate assessment possible. Most of the time, those assessments help avoid unnecessary panic while still protecting communities if conditions deteriorate. That careful balance is exactly why monitoring agencies update volcanic alert levels gradually, rather than reacting dramatically to every ash plume. Because the objective is not to create fear. The objective is to recognize meaningful change before it becomes irreversible. And beneath Anak Krakatau, one factor complicates every one of those calculations. This volcano is not simply growing upward, it is growing outward as well. Every eruption adds fresh volcanic rock to steep slopes built on foundations that are already partially surrounded by the sea. Some layers cool into strong lava flows, others consist of loose ash, fragmented rock, and unstable debris that can be surprisingly weak despite appearing solid from a distance. Over years of repeated eruptions, those layers create an island that is constantly rebuilding itself. But every new layer also adds more weight, more stress, more imbalance, and gravity never stops pulling. That may sound like an engineering problem rather than a volcanic one. In reality, it is both. Because the greatest danger at Anak Krakatau is not necessarily how violently it erupts. It is whether the mountain itself can continue supporting the enormous structure it has spent decades building. And history has already shown what can happen when the answer to that question suddenly becomes no. Gravity is the one force no volcano can ever escape. Every eruption at Anak Krakatau adds another layer of lava, ash, volcanic bombs, and fragmented rock onto an island that did not even exist a century ago. Unlike ancient mountains that have spent thousands or even millions of years weathering into relatively stable forms, Anak Krakatau is still under construction. Every explosive event changes its shape. Every lava flow alters the distribution of weight. Every collapse creates new weaknesses. It is one of the youngest major volcanic islands on Earth, and that youth is one of its greatest dangers. When most people picture a volcano, they imagine a solid cone of rock rising from the ground. In reality, volcanoes are far less uniform than they appear. Their interiors resemble enormous construction sites, built over countless eruptions. Thick lava flows form strong foundations in some places, while nearby layers may consist almost entirely of loose ash, pumice, and fragmented volcanic debris that never truly bonds into solid rock. Imagine constructing a skyscraper by alternating reinforced concrete floors with layers of gravel. From the outside, the building might appear perfectly stable. Inside, however, its structural strength would vary dramatically from one section to another. Volcanoes develop in much the same way. Each eruption deposits different materials under different conditions. Lava that cools slowly can become dense and relatively strong. Explosive eruptions scatter lighter fragments that accumulate in unstable piles. Rainwater seeps into those deposits. Hot volcanic gases alter minerals through chemical reactions. Fractures develop as the volcano repeatedly heats and cools. The result is a mountain filled with hidden weaknesses. Now place that mountain on an island surrounded by the sea. The ocean is not simply sitting beside Anak Krakatau. It is actively reshaping it every single day. Waves erode the shoreline. Storms undercut steep slopes. Salt water infiltrates fractures. Currents remove loose material from the base of the island. Even during periods when the volcano appears relatively quiet, the surrounding ocean is constantly modifying the foundation supporting the cone above. This interaction between volcanic growth and marine erosion creates an unstable balance. One process builds, the other tears down. As long as those processes remain roughly balanced, the volcano continues evolving without catastrophic failure. But balance can disappear surprisingly quickly. Volcanologists describe this using the concept of slope stability. Every hillside has a point at which gravity overcomes the strength of the material holding it together. Engineers calculate similar limits when designing dams, highways, and retaining walls. They refer to something called the factor of safety, a measure of how much stronger a structure is than the forces trying to make it fail. Volcanoes have no engineers reinforcing them. Their factor of safety changes constantly. Fresh eruptions increase weight. Earthquakes shake the slopes. Rainwater saturates loose deposits. Heat alters rock strength. New fractures develop. Old fractures widen. Slowly, often invisibly, the margin between stability and collapse becomes thinner. Sometimes that process unfolds over decades. Sometimes it accelerates over only weeks. One of the reasons Anak Krakatau receives such close scientific attention is because satellite imagery has shown that the island does not simply grow upward in a symmetrical fashion. Different eruptions feed different parts of the cone. Lava may accumulate more heavily on one flank than another. Explosive events may excavate one side while leaving the opposite slope largely intact. This uneven growth matters enormously. Think about balancing a stack of books directly over the center of a table. Now slide several heavy books toward one edge. The entire stack becomes less stable even though the total weight has not changed. Volcanoes experience the same principle. Weight distributed unevenly creates additional stress within the cone. That stress alone does not guarantee collapse, but it increases vulnerability when combined with other factors. Then there is hydrothermal alteration. This is one of the least appreciated processes affecting volcanic stability, yet it plays a crucial role in many collapses around the world. Hot volcanic gases and heated groundwater circulate through fractures inside the volcano for years. Those fluids gradually alter the minerals making up the surrounding rock. Strong volcanic rock can slowly transform into much weaker clay-rich material. From the outside, nothing appears different. Inside, however, portions of the mountain may be losing much of their structural strength. It is somewhat like termites weakening the wooden frame of a house. The exterior still looks intact. The internal support system is quietly deteriorating. Researchers studying volcanic collapses have repeatedly found evidence that hydrothermal alteration weakened large sections of volcanic edifices before failure occurred. That is one reason why geologists collect rock samples, map alteration zones, and monitor thermal activity so carefully. The visible eruption is only part of the hazard. The hidden structural changes may ultimately determine how dangerous the eruption becomes. Rainfall introduces another layer of complexity. Indonesia's tropical climate delivers enormous amounts of precipitation throughout much of the year. Heavy rain infiltrates porous volcanic deposits, increasing their weight while simultaneously reducing friction between particles. Water can also generate internal pore pressure, making already unstable slopes even more susceptible to movement. Picture walking across dry sand at the beach. Now imagine that same slope after powerful waves have saturated it. The behavior changes dramatically. Volcanic slopes respond in similar ways. Rain alone rarely causes catastrophic flank collapse. But when combined with fresh volcanic deposits, earthquakes, gas-driven fracturing, and ongoing magma movement, it can become another important piece of the puzzle. Scientists therefore monitor weather almost as carefully as volcanic activity itself. Then there is seismic shaking. Indonesia experiences thousands of earthquakes every year because of its position along multiple active plate boundaries. Most are small. Many occur far from Anak Krakatau. Some are related directly to volcanic processes, while others originate from tectonic movement along the Sunda megathrust. Each earthquake sends vibrations through the volcanic edifice. Most do little measurable damage. Occasionally, however, repeated shaking gradually weakens already fractured rock masses. Imagine bending a paperclip back and forth. One bend changes very little. Repeated stress eventually causes failure. Rock behaves differently than metal, but the principle of cumulative weakening remains surprisingly similar. None of these individual processes automatically means disaster. Uneven growth, marine erosion, hydrothermal alteration, heavy rainfall, earthquakes, gas pressure, fresh lava accumulation, each one can occur without triggering collapse. The concern arises when several begin operating together. Volcanologists often refer to cascading hazards. Instead of one event causing one consequence, one process increases the probability of another, which then creates the conditions for something even larger. An eruption deposits unstable material, rain saturates it, earthquakes fracture it further, gas pressure continues building, a section of the slope weakens, gravity finally takes over. The result is no longer simply an eruption, it becomes a structural failure, and structural failures involving island volcanoes introduce an entirely different category of danger. Because when millions of tons of volcanic rock suddenly enter the ocean, the water itself becomes part of the disaster. Unlike earthquake-generated tsunamis, which begin with movement of the seafloor, volcanic tsunamis can originate from collapsing volcanic flanks, underwater explosions, pyroclastic flows entering the sea, or combinations of several mechanisms occurring almost simultaneously. The ocean does not care what displaced it. It responds to the displacement itself. That distinction became tragically important in late 2018. At first, many people assumed the tsunami must have been triggered by an earthquake. There wasn't one. Instead, investigators eventually pieced together a sequence that fundamentally changed how scientists viewed Anak Krakatau. A large section of the volcano had failed catastrophically, sliding into the surrounding sea and displacing enough water to generate deadly tsunami waves that struck nearby coastlines with devastating speed. The eruption was only one chapter of the disaster. The collapse was another, and together they revealed why this volcano cannot be evaluated using eruption intensity alone. Today, every ash plume, every shallow earthquake, every burst of volcanic tremor, and every subtle change in the shape of the island is interpreted through the lessons learned from that event. Because researchers now understand something they did not fully appreciate before. The greatest threat may arrive not from what rises into the sky, but from what suddenly disappears beneath the sea. And to understand why today's renewed activity immediately brings back memories of that catastrophe, we have to examine exactly what happened during those extraordinary hours in December 2018, when an eruption transformed into one of the deadliest volcanic tsunamis of the modern era. On the evening of December 22nd, 2018, there was no giant earthquake to warn the people living around the Sunda Strait. No violent shaking sent families running into the streets. No emergency alert announced that a massive section of a volcano had just collapsed into the sea. That absence of a familiar warning became one of the defining characteristics of the disaster. For generations, many people associated tsunamis with large earthquakes. Feel the ground shake, move to higher ground. It was a life-saving rule, reinforced by countless disaster preparedness campaigns after the devastating Indian Ocean tsunami of 2004. But on that December night, the Earth remained largely silent. The ocean did not. Anak Krakatau had been active for months leading up to the event. Frequent eruptions were sending ash into the atmosphere, lava was accumulating on parts of the volcanic cone, and scientists were closely monitoring the continuing activity. None of those observations were unusual for the volcano. Anak Krakatau had built a reputation for persistent eruptive behaviour throughout much of its young existence. What nobody knew was exactly how unstable part of the volcano had become. At some point during the evening, a large section of the southwestern flank catastrophically failed. Millions of cubic meters of volcanic rock suddenly detached from the island and plunged into the surrounding waters of the Sunda Strait. Imagine dropping an enormous mountain into a bathtub. The water has only one place to go, outward. Of course, the Sunda Strait is not a bathtub, and tsunami physics is far more complex than a simple splash, but the basic principle remains the same. A massive, rapid displacement of water generates waves that radiate away from the source. Unlike ordinary wind-driven waves, tsunami waves involve movement throughout the entire water column, from the surface to the seafloor. That gives them extraordinary energy. The collapse happened quickly, the tsunami travelled quickly. For many coastal communities, warning time was measured in minutes. That fact alone fundamentally changed how scientists think about volcanic tsunami hazards. Traditional tsunami warning systems are designed primarily around earthquakes. Networks of seismometers detect large tectonic events almost immediately. Computer models estimate tsunami generation based on earthquake magnitude, depth, and fault geometry. Alerts can then be issued to populations at risk. But a volcanic flank collapse is different. If there is no major earthquake, there may be no automatic trigger for many warning systems. In 2018, this gap became painfully obvious. Communities along the coasts of Java and Sumatra were struck with little or no meaningful warning. Beaches that had been filled with tourists and families enjoying the evening suddenly became disaster zones. Concert stages, hotels, restaurants, fishing villages, and residential neighbourhoods were overwhelmed as powerful waves pushed inland. More than 430 people lost their lives. Thousands more were injured. Tens of thousands were displaced from their homes. The human cost extended far beyond the immediate casualties. Entire communities faced destroyed infrastructure, damaged livelihoods, contaminated water supplies, and months of recovery. Fishing fleets were damaged or destroyed. Coastal businesses disappeared overnight. Roads became impassable. Emergency responders worked through darkness, debris, and continuing volcanic activity to reach survivors. For volcanologists, however, another question immediately emerged. How much of the volcano had actually collapsed? Answering that question required a combination of satellite imagery, aerial surveys, bathymetric mapping, drone observations, and geological modelling. As researchers compared images taken before and after the disaster, the scale of the structural failure became increasingly clear. The volcano itself had changed shape. A substantial portion of the cone was simply gone. The summit elevation dropped dramatically. Large sections of the southwestern flank had disappeared beneath the sea, leaving behind a radically altered volcanic landscape. It was one of the clearest modern examples of how rapidly a volcanic island can reorganize itself. The eruption had not merely produced ash, it had physically rebuilt the volcano. This realization carried enormous scientific importance because it demonstrated that relatively moderate eruptive activity could still produce catastrophic consequences if structural collapse occurred at the wrong moment. In other words, eruption size alone was not the deciding factor. Geometry was, timing was, slope stability was, the interaction between magma and gravity was. This shifted the focus of hazard assessment around Anak Krakatau almost overnight. Previously, many discussions centered primarily on explosive eruption scenarios, ash clouds, pyroclastic material near the volcano, volcanic lightning, aviation hazards, and ballistic ejecta. Those hazards remain real. But after 2018, scientists expanded the conversation. Every assessment now had to include a second question. Could part of the volcano collapse? Notice how different that question is. It is no longer asking whether pressure underground is increasing. It is asking whether the mountain itself remains mechanically stable while that pressure changes. Those are related problems, but they are not identical. Researchers studying the collapse also investigated why the failure occurred where it did. Several contributing factors were identified, although, as with many geological events, no single explanation accounts for everything. Repeated eruptive activity had built fresh volcanic deposits on parts of the cone. The volcano's rapid growth produced steep slopes. Internal hydrothermal alteration likely weakened some rock units. Magma movement may have contributed to additional instability. Gravity continued acting on the entire structure throughout the process. Eventually, the combined stresses exceeded the strength of the weakened flank. Failure became inevitable. One of the remarkable aspects of geology is that enormous disasters often result not from one extraordinary cause, but from many ordinary processes operating together over time. That is exactly what appears to have happened here. No individual eruption necessarily doomed the volcano. No single earthquake pushed it over the edge. No isolated rainfall event caused the collapse. Instead, years of gradual change accumulated until the structure reached its limit. Then, within moments, decades of instability were released. This concept appears repeatedly throughout Earth science. Snow accumulates quietly before an avalanche. Stress builds silently before a fault ruptures. Water rises gradually behind a weakened dam. The final collapse seems sudden. The preparation took years. That perspective is crucial when interpreting activity today. Every time scientists observe fresh lava building one side of Anak Krakatau, every time they map changes in crater geometry, every time satellites reveal alterations to the island's outline, they are asking whether those changes are increasing or decreasing structural stability, not because they expect another collapse tomorrow, but because they know with certainty that collapse is physically possible. Another important lesson emerged from 2018. Hazards can evolve faster than public awareness. Many residents understandably focused on the visible eruption taking place offshore. Ash clouds are dramatic. Lava fountains attract attention. Explosions dominate headlines. What remained largely invisible was the gradual weakening of the volcano's internal structure. the greatest threat was developing beneath the surface and beneath the waterline. That realization has reshaped monitoring priorities ever since. Today, satellites repeatedly image the island. Radar systems measure deformation. Scientists compare shoreline positions. Thermal cameras monitor eruptive vents. Seismic instruments record every significant volcanic earthquake. Gas measurements track changes in degassing, not because each observation predicts disaster by itself, but because together they provide the best opportunity to recognize meaningful changes before another cascading sequence develops. Still, one question remains remarkably difficult to answer. Could today's activity follow the same path as 2018, or has the volcano entered an entirely different phase of its evolution? That is where modern monitoring becomes both incredibly powerful and frustratingly limited. Because while scientists can observe the volcano in greater detail than ever before, nature still refuses to reveal every answer in advance. And that uncertainty is exactly what brings us to the question everyone is asking now. How closely does today's unrest actually resemble the conditions that existed before the 2018 collapse? The question dominating nearly every discussion about Anak Krakatau today is remarkably simple. Are we witnessing the same sequence of events that preceded the devastating 2018 tsunami? Or is this simply another period of elevated volcanic activity that will gradually subside? It is a natural question, but it is also one that requires careful interpretation. One of the biggest misconceptions about volcanoes is the belief that they repeat themselves like clockwork, following identical patterns every time they become active. In reality, no two eruptions are ever exactly alike. Every eruption changes the volcano itself by altering its internal plumbing, reshaping its summit, depositing new layers of lava and ash, and sometimes removing entire sections of the cone. That means Anak Krakatau today is not the same volcano it was before 2018, and any comparison must focus on broader geological patterns rather than expecting history to unfold scene for scene. That is precisely how volcanologists approach the problem. Instead of searching for one dramatic warning sign, they compare dozens of independent observations collected over weeks and months. They examine whether volcanic earthquakes are becoming more frequent, whether harmonic tremor is becoming more persistent, whether gas emissions suggest fresh magma is rising, whether satellite imagery detects inflation of the volcanic edifice, and whether repeated eruptions are changing the overall shape of the island. None of these observations alone proves that a dangerous event is approaching, but taken together they can reveal whether the volcano's behavior is evolving in a meaningful way. The goal is not to predict a single eruption or collapse on a specific day, but to determine whether the overall probability of increasingly hazardous scenarios is changing. One of the strongest similarities between today's activity and the period before the 2018 disaster is the persistence of volcanic unrest itself. Anak Krakatau remains an active volcano that continues to generate ash emissions, explosive bursts, volcanic earthquakes, and thermal anomalies. Persistent eruptive activity has always been part of the volcano's character, and in isolation it is not considered unusual. That distinction is extremely important, because headlines often imply that any visible eruption represents an immediate catastrophe waiting to happen. Scientists know better. Anak Krakatau has produced countless ash plumes and moderate eruptions without triggering major structural failure. What concerns researchers is not the existence of activity, but whether that activity begins changing in ways that suggest increasing instability beneath or within the volcano. This is where historical context becomes indispensable. Before the 2018 collapse, Anak Krakatau had spent months erupting and gradually adding new volcanic material to parts of its cone. Each eruption subtly altered the island's shape, increasing the weight carried by already steep slopes while repeated explosions continued to fracture the volcanic structure. Researchers now know that these gradual changes were likely contributing factors in the eventual collapse, even though they did not appear extraordinary at the time. Looking back with the benefit of hindsight, it is easy to identify a chain of events that eventually led to disaster. Looking forward in real time is far more difficult, because volcanoes frequently produce similar periods of unrest that never progress beyond moderate eruptive activity. That uncertainty is exactly why scientists avoid drawing direct conclusions from any single observation. There are also important differences between the conditions before the 2018 tsunami and the volcano that exists today. The collapse fundamentally transformed Anak Krakatau by removing a large portion of its southwestern flank and dramatically lowering its summit. Since then, repeated eruptions have slowly rebuilt much of the volcanic cone, creating an island with a different geometry, different internal pathways for magma, and a different distribution of weight than existed before the collapse. In other words, today's Anak Krakatau is effectively a reconstructed volcano. It is still connected to the same magma system, but its physical structure has changed enough that scientists cannot simply compare current satellite images with those from 8 years ago and expect identical behaviour. Every new eruption is building on a foundation that no longer matches the one that failed in 2018. Monitoring capabilities have also improved significantly since that disaster. Satellite constellations now revisit the volcano more frequently. Radar systems can detect minute changes in the volcano's shape. With greater precision, thermal imaging provides better information about surface heat, and increasingly sophisticated computer models allow researchers to combine seismic, geodetic, gas, and visual observations into a much more complete picture of what is happening beneath the surface. Perhaps even more valuable than technological improvements is the experience gained from the 2018 collapse itself. Scientists now understand that flank stability must be evaluated alongside eruptive activity, meaning every noticeable change in the volcano's shape receives far closer attention than it might have before. Fresh lava accumulating on one side of the cone, newly developed fractures, changes in shoreline geometry, and shifts in eruptive vents are all examined because they may gradually influence the volcano's long-term structural stability. Even with these advances, however, volcanology remains a science built on probabilities rather than certainties. Researchers can identify increasing risk, recognize meaningful changes, and estimate the likelihood of different scenarios, but they cannot determine the exact day when a volcanic collapse or major eruption will occur. This often frustrates people looking for definitive answers, yet it reflects the reality of how natural systems behave. Volcanoes evolve continuously, and many of the processes that ultimately determine their behavior take place kilometers beneath the surface, where direct observation is impossible. Scientists therefore rely on multiple lines of indirect evidence, updating their assessments whenever new information becomes available, instead of treating any forecast as permanent. Perhaps the most important lesson from both 2018 and today's renewed activity is the difference between possibility and probability. Another major flank collapse at Anak Krakatau is unquestionably possible, because the volcano has already demonstrated that it can happen. At the same time, the volcano showing ongoing eruptive activity does not mean another catastrophic collapse is inevitable or imminent. Those two statements are not contradictory. They are the foundation of responsible hazard assessment. A real hazard deserves serious attention even when its timing remains uncertain. This balance between vigilance and restraint is exactly why Indonesian monitoring agencies continue observing every change at Anak Krakatau so closely. They are not waiting for dramatic confirmation after a disaster begins. They are searching for subtle changes that might provide communities with valuable time if the volcano's behavior begins shifting toward a more dangerous phase. That brings us to perhaps the most critical question of all. If the volcano were to produce another major structural failure, the greatest challenge would no longer be understanding the geology. It would be protecting the millions of people who live, work, travel, and fish along the shores of the Sunda Strait. The science of monitoring is only one half of the equation. The other half is ensuring that warnings, evacuation plans, and public preparedness are capable of turning those scientific observations into lives saved when every minute counts. The most frightening aspect of a tsunami generated by Anak Krakatau is not necessarily its size. It is the amount of time people may have to react. When most people think about tsunamis, they picture the devastating Indian Ocean disaster of 2004. That event began with one of the largest earthquakes ever recorded, giving scientists a clear seismic signal that something extraordinary had occurred beneath the seafloor. Although warning systems were far less developed than they are today, the earthquake itself provided an unmistakable indication that a tsunami was possible. A volcanic tsunami generated by Anak Krakatau can be very different. If a large section of the volcano were to collapse into the Sunda Strait, there may be no massive tectonic earthquake to trigger conventional warning systems. Instead, the tsunami would be created by the sudden displacement of enormous volumes of seawater, meaning nearby coastlines could face an extremely compressed timeline between the collapse itself and the arrival of destructive waves. The geography of the Sunda Strait makes this hazard particularly challenging. The strait separates the Indonesian islands of Java and Sumatra, two of the most densely populated islands on Earth. Millions of people live within the broader region, while countless others depend on the surrounding waters every day for fishing, transportation, tourism, and trade. Ferries regularly cross the strait, connecting communities that rely on this maritime corridor as part of daily life. Along the coastline are fishing villages, ports, industrial facilities, hotels, beach resorts, and residential neighbourhoods, many of them located only a few metres above sea level. Unlike communities facing distant ocean basin tsunamis, these coastal populations are situated relatively close to the source of the potential hazard. That proximity dramatically reduces the time available for evacuation if a tsunami develops. The speed of a tsunami often surprises people because the waves visible near the shoreline bear little resemblance to the dramatic breakers seen in popular movies. In deep water, tsunami waves may travel at speeds comparable to a commercial jet aircraft while remaining only modest in height, making them almost impossible for ships to recognize in the open ocean. As the waves approach shallower coastal waters, however, the lower portion of the wave begins interacting with the seabed, causing it to slow while the energy behind it continues moving forward. The result is a rapid increase in wave height and destructive power as the tsunami approaches land. This process, known as shoaling, explains why a wave that seems insignificant far offshore can become devastating once it reaches the coastline. The shape of the coastline itself also plays an important role in determining the severity of tsunami impacts. Certain bays, harbours, and inlets can concentrate incoming wave energy, producing significantly higher water levels than neighbouring stretches of coastline. Local underwater topography influences how waves refract, reflect, and combine, meaning communities separated by only a few kilometres may experience very different levels of flooding during the same event. This complexity makes tsunami forecasting extraordinarily difficult because emergency managers must account not only for the size of the initial wave, but also for how local geography will modify its behaviour before it reaches populated areas. One of the greatest lessons from the 2018 disaster was that many victims never realised a tsunami was approaching. There was no prolonged ground shaking to prompt immediate evacuation, and in several locations the first indication of danger came only when people noticed unusual movement along the shoreline or saw the wave itself. By then, precious minutes had already been lost. This is why disaster preparedness experts increasingly emphasise that official warnings, while critically important, should never be the only trigger for action. If authorities issue evacuation orders because of significant volcanic activity or evidence of a developing tsunami, those instructions should be followed immediately rather than waiting for visual confirmation. Waiting to see the wave may eliminate the opportunity to escape altogether. Indonesia has invested heavily in strengthening its disaster monitoring capabilities since 2018. Volcanic monitoring stations continue tracking Anak Krakatau around the clock, while seismic networks, satellite observations, radar systems, and coastal monitoring equipment all contribute to a much more comprehensive understanding of changing conditions than was available only a decade ago. Emergency management agencies have also expanded public education campaigns, evacuation planning, and hazard mapping for communities located near high-risk coastlines. These improvements do not eliminate the hazard, but they significantly improve the likelihood that dangerous changes can be identified and communicated more quickly than in the past. Even so, no monitoring system can overcome the laws of physics. If a large volcanic flank were to collapse directly into the Sunda Strait, communities nearest the source would still face an extremely limited window in which to respond. This reality places enormous importance on preparedness before any emergency begins. Residents living in tsunami-prone areas benefit from knowing evacuation routes in advance, identifying nearby high ground, understanding official alert procedures, and discussing emergency plans with family members before a crisis develops. Tourists visiting coastal resorts should also familiarise themselves with local evacuation signage, rather than assuming hotel staff or emergency services will always have enough time to provide individual instructions during a rapidly unfolding event. Another important misconception involves the behaviour of tsunami waves after the first impact. Many people believe that surviving the initial wave means the danger has passed. In reality, tsunamis often arrive as a series of waves separated by several minutes or even longer intervals and later waves can be larger than the first. Water that initially recedes may suddenly return with even greater force, carrying debris, vehicles, boats, and damaged structures inland. Emergency officials consistently advise people to remain on high ground until authorities declare the area safe, because returning too early has repeatedly led to additional casualties in tsunami disasters around the world. For people at sea, the situation can be very different depending on location. Vessels already in deep water are often safer remaining offshore than attempting to race back toward a harbour where tsunami effects become much stronger. By contrast, boats located close to the shoreline or inside ports may have little time to react before rapidly changing water levels and powerful currents create extremely hazardous conditions. This is one reason maritime authorities closely monitor volcanic activity and maintain communication procedures for commercial shipping operating near the Sunda Strait. Ultimately, the greatest defense against a volcanic tsunami is not predicting its exact timing, but reducing the number of decisions people must make under extreme pressure. Communities that already know where to go, how to recognize official warnings, and why immediate evacuation matters consistently perform better than communities forced to improvise during an unfolding emergency. That philosophy has shaped disaster preparedness efforts across Indonesia since 2018, transforming one of the region's most painful lessons into an opportunity to reduce future risk. Yet despite all these preparations, one challenge remains impossible to eliminate entirely. Scientists can observe the volcano with unprecedented precision, but they cannot see directly into the magma system beneath it, nor can they predict every structural change before it occurs. That unavoidable uncertainty is why volcanologists rarely speak in absolutes, and why understanding the limits of modern forecasting is just as important as understanding its remarkable strengths. One of the hardest realities for the public to accept is that even with satellites orbiting Earth every hour, sophisticated seismic networks, artificial intelligence, drones, thermal cameras, gas sensors, and some of the world's most experienced volcanologists watching a Krakatau around the clock, nobody can say with certainty when the next major collapse or eruption will occur. That is not a failure of science. It is a reflection of the extraordinary complexity of volcanic systems. Unlike a mechanical device with predictable components, a volcano is a constantly evolving natural structure whose internal plumbing changes with every eruption. Magma opens new fractures, seals old conduits, alters gas pathways, weakens surrounding rock, and reshapes the mountain itself. Scientists can measure many of these changes indirectly, but they cannot directly observe every process taking place several kilometers beneath the surface. That unavoidable limitation means every volcanic forecast is expressed in terms of probability rather than certainty. This is why official volcanic monitoring agencies are careful about the language they use. They rarely announce that a major eruption will happen on a specific day, because the available evidence almost never supports that level of confidence. Instead, they describe changes in activity, evaluate whether hazards are increasing or decreasing, and adjust alert levels when the balance of evidence shifts. These alert levels are often misunderstood by the public. A higher alert level does not necessarily mean a catastrophic eruption is imminent, just as a lower alert level does not mean the volcano has become harmless. Alert systems are designed to communicate the current level of observed unrest and the precautions that should accompany it. They are tools for managing risk, not guarantees about the future. Scientists also distinguish between confidence in observations and confidence in forecasts. Their confidence that Anak Krakatau is currently active is extremely high, because that conclusion is supported by multiple independent observations. Ash emissions can be seen directly, seismic instruments detect volcanic earthquakes, satellites monitor thermal anomalies, and gas measurements confirm ongoing degassing. There is little uncertainty that the volcano remains active. The uncertainty begins when researchers attempt to determine what those observations mean for the weeks or months ahead. Will the current activity gradually decline? Will it continue at roughly the same level? Will fresh magma enter the system and increase eruptive intensity? Could structural instability eventually develop into another flank collapse? Each of these scenarios is physically possible, but the available evidence rarely points exclusively toward only one outcome. To address this uncertainty, volcanologists increasingly rely on multiple models rather than a single forecast. Different research groups may emphasize different datasets depending on their expertise. Some focus primarily on seismic patterns, looking for changes in earthquake frequency, depth, or energy that could indicate magma migration. Others specialize in satellite deformation measurements, searching for subtle inflation or deflation of the volcanic edifice that might reveal changes in underground pressure. Gas geochemists analyze sulfur dioxide and carbon dioxide emissions for evidence that fresh magma is ascending. Structural geologists study the volcano's evolving slopes, mapping fractures, and assessing how repeated eruptions are affecting long-term stability. None of these approaches is sufficient by itself, but together they create a far more complete picture of the volcanic system than any single observation could provide. This collaborative approach is particularly important because volcanoes often produce conflicting signals. A period of increasing seismic activity may occur without significant ground deformation. Elevated gas emissions may accompany only modest eruptive activity. A volcano may inflate for weeks before suddenly stabilizing without producing a large eruption. Conversely, some eruptions occur after surprisingly subtle precursors. Nature does not always provide a neat sequence of escalating warning signs, which is why scientists continually update their interpretations as new information becomes available. Forecasting a volcano is much like assembling a puzzle, whose pieces are constantly changing shape, while some remain permanently hidden beneath the table. One of the greatest strengths of modern volcanology is the use of ensemble thinking rather than reliance on a single prediction. Instead of asking, "What is going to happen?" researchers increasingly ask, "What are the most plausible scenarios, and how likely is each one based on the evidence we have today?" This approach is familiar to meteorologists forecasting hurricanes or severe thunderstorms. A hurricane forecast cone does not guarantee the storm will follow one exact path. It illustrates a range of possible outcomes supported by available data. Volcanologists apply similar reasoning by evaluating multiple future scenarios simultaneously. A continued period of moderate eruptive activity may currently appear more likely than a major structural collapse, but the less likely scenario still receives careful attention because its consequences would be far greater if it occurred. Public communication becomes especially challenging whenever uncertainty is high. If scientists emphasize only the worst-case scenario, communities may experience unnecessary panic, economic disruption, and eventually lose confidence if the feared event does not occur. If they emphasize only the most likely outcome, people may underestimate low probability but high consequence hazards that still deserve serious preparation. Responsible scientific communication therefore requires striking a careful balance between caution and restraint. The goal is neither to reassure people falsely nor to frighten them unnecessarily. It is to explain clearly what the evidence supports, what remains unknown, and what practical actions should be taken regardless of which scenario ultimately unfolds. Anak Krakatau illustrates this balance better than almost any volcano on Earth, because its history contains both routine activity and extraordinary disasters. Most eruptive episodes pass without producing catastrophic consequences beyond the immediate vicinity of the volcano. At the same time, the 2018 flank collapse demonstrated that even a relatively localized structural failure could generate a deadly tsunami, affecting distant coastlines within minutes. Scientists cannot ignore that history simply because it is uncommon, yet neither can they assume every new ash plume marks the beginning of another catastrophe. Every period of unrest must therefore be evaluated on its own evidence while remaining informed by everything researchers have learned from previous events. This careful, evidence-based approach sometimes disappoints people looking for certainty, but uncertainty is not the same as ignorance. Modern volcanology has dramatically improved humanity's ability to recognize changing hazards, identify increasing instability, and provide earlier warnings than would have been possible only a few decades ago. At the same time, honest scientists openly acknowledge the limits of their knowledge, because doing so strengthens rather than weakens public trust. Confidence should come not from pretending uncertainty does not exist, but from demonstrating that every available observation is being collected, analysed, and compared continuously as conditions evolve. Unfortunately, uncertainty often creates a vacuum that misinformation quickly fills. Whenever a volcano attracts global attention, alternative explanations begin spreading across social media, ranging from claims that governments are manipulating the weather to suggestions that secret technologies or unusual activity on the sun are somehow responsible for the eruption. These theories frequently gain traction precisely because volcanic systems are so complex. If people do not understand what scientists know and what they do not know, they become more vulnerable to explanations that sound simple but have no basis in geology or physics. Separating genuine scientific uncertainty from unsupported speculation has therefore become an increasingly important part of communicating volcanic hazards, and that is exactly where the story turns next. Whenever a major natural disaster begins dominating headlines, another phenomenon almost always follows close behind. Long before scientists have finished analysing new data, social media fills with confident claims explaining what is really happening. Some argue that governments are secretly triggering eruptions through geoengineering projects. Others insist that powerful radio transmitters such as HAARP are somehow manipulating volcanoes from thousands of kilometres away. Still others point to unusual activity on the Sun, planetary alignments, or mysterious energy fields as the hidden force driving eruptions around the world. These explanations often spread rapidly because they offer something people naturally crave during periods of uncertainty: simple answers. Unfortunately, nature is rarely simple, and in the case of Anak Krakatau, nearly everything scientists have observed points toward a much more straightforward and far more fascinating explanation rooted in geology. To understand why these alternative claims fail, it helps to return to the foundation of the volcanic system itself. Anak Krakatau exists because of plate tectonics, one of the best established theories in all of Earth science. The Indo-Australian plate continues moving beneath the Eurasian plate at a rate of several centimetres each year. That movement has been measured directly using satellite-based GPS networks and has been confirmed through decades of geological, seismic and geophysical research. As the descending oceanic plate sinks deeper into the mantle, it releases water trapped within its minerals. This water lowers the melting point of the overlying mantle, allowing magma to form. The magma gradually rises through Earth's crust because it is less dense than the surrounding rock, feeding the chain of volcanoes stretching across Indonesia. Anak Krakatau is one visible expression of a process that has been operating for millions of years and continues regardless of political events, technological developments, or human activity. One of the most persistent misconceptions involves the idea that cloud seeding or weather modification somehow influences volcanic eruptions. These are two entirely different systems operating in completely different parts of the Earth. Cloud seeding, where it is used, attempts to encourage precipitation by introducing microscopic particles into existing clouds several kilometers above the surface. Volcanic eruptions originate from magma reservoirs and tectonic processes extending kilometers beneath the ground. The scale, energy, and physical mechanisms involved are so vastly different that there is no credible scientific evidence connecting routine weather modification techniques to the movement of magma beneath an active volcano. Rainfall can influence certain surface processes, such as landslides or erosion, but it does not generate magma, create tectonic plate movement, or suddenly trigger deep volcanic systems that have been evolving for decades. Another claim that often resurfaces during periods of volcanic unrest is that unusual solar activity is somehow causing eruptions. The sun certainly affects Earth in important ways. Powerful solar storms can interfere with satellites, disrupt radio communications, influence navigation systems, and produce spectacular auroras at high latitudes. Scientists monitor these events continuously through spacecraft and observatories dedicated to studying space weather. However, the mechanisms responsible for solar storms are fundamentally different from those driving volcanism. A burst of charged particles from the sun interacts primarily with Earth's magnetic field and upper atmosphere. Magma movement inside Anak Krakatau is governed by heat, pressure, rock mechanics, and plate tectonics deep within Earth's interior. Extensive research has not established a causal relationship, showing that ordinary variations in solar activity initiate volcanic eruptions. While scientists continue investigating many subtle interactions within the Earth system, the evidence overwhelmingly indicates that Anak Krakatau's current behaviour is controlled by geological processes beneath Indonesia rather than events occurring 150 million kilometres away. HAARP, another frequent subject of online speculation, provides a useful example of how technical terminology can be misunderstood. The facility was designed for research into the Earth's ionosphere, the electrically charged region of the upper atmosphere that affects radio communications and space weather. its transmitted energy is minuscule compared with the immense forces operating inside Earth's crust. The energy released during even a modest volcanic eruption exceeds anything produced by human radio transmission systems by many orders of magnitude. More importantly, there is no physically plausible mechanism through which ionospheric research could manipulate magma chambers buried beneath kilometers of rock. Extraordinary claims require extraordinary evidence, and despite years of speculation, no credible geological or geophysical evidence has demonstrated such a connection. Part of the reason these theories remain popular is psychological rather than scientific. Human beings are remarkably good at recognizing patterns, even when those patterns do not actually represent cause and effect. If a volcanic eruption occurs shortly after an unusual astronomical event or a widely reported solar flare, it is tempting to connect the two simply because they happened close together in time. Scientists work very hard to avoid this trap by asking a different question: what mechanism links these events? Without a plausible physical process supported by observations and reproducible evidence, coincidence alone does not establish causation. This disciplined approach is what separates scientific investigation from speculation. Ironically, the real explanation for Anak Krakatau's activity is arguably more remarkable than any conspiracy theory, because it involves processes operating on scales almost beyond human imagination. Consider the journey of a fragment of oceanic crust descending beneath Indonesia. Over millions of years, that rock travels deep into the mantle, where increasing temperatures and pressures alter its minerals and release water into the surrounding mantle. New magma forms, slowly rising through fractures in the crust while accumulating in underground reservoirs. Eventually, pressure, gas content, and rock strength reach conditions that allow part of that magma to erupt at the surface. What appears as a sudden explosion visible from space is actually the latest moment in a geological story that has been unfolding for vast spans of time. No hidden technology is required. Earth's own internal engine is more than capable of producing these extraordinary events on its own. This does not mean scientists have solved every mystery surrounding volcanoes. Far from it. Researchers continue studying why seemingly similar volcanoes behave so differently, why some magma chambers remain stable for decades while others erupt repeatedly, and exactly what combinations of processes lead to catastrophic flank collapses like the one witnessed in 2018. Acknowledging these unanswered questions is not a weakness of science, it is one of its greatest strengths. Science advances by identifying uncertainty, testing competing explanations against evidence, and revising conclusions whenever new data become available. Unsupported claims, by contrast, typically begin with a conclusion and then search selectively for information that appears to support it, while ignoring contradictory evidence. For people living around Anak Krakatau, the practical implications are clear. The most reliable source of information remains Indonesia's official volcanic monitoring agencies, supported by international scientific collaboration and continuously updated observations from satellites, seismic networks, gas monitoring stations, and field investigations. These organizations may not always provide the certainty people hope for, but they provide something far more valuable: conclusions grounded in measurable evidence rather than speculation. In situations where public safety depends on timely decisions, evidence is infinitely more useful than certainty built on unsupported assumptions. Once the distractions of misinformation are set aside, the focus returns to the challenge that matters most. Scientists understand why Anak Krakatau exists, they understand the tectonic forces feeding it, and they understand many of the warning signs that precede changing volcanic behavior. The remaining question is not whether hidden forces are controlling the volcano. It is whether the systems designed to protect nearby communities are prepared if nature decides to demonstrate its own power once again. That brings us to Indonesia's remarkable effort to monitor one of the most dangerous volcanic regions on Earth, and the enormous responsibility of turning scientific observations into decisions that can save lives. Living with an active volcano is very different from simply studying one. For scientists, Anak Krakatau is a constantly evolving geological system that must be monitored, measured, and understood. For the people living around the Sunda Strait, however, it is also a permanent neighbour. Fishing boats leave the harbours each morning with the volcano visible on the horizon. Ferries cross the strait beneath its ash clouds. Families build homes, operate businesses, and raise children in communities that have existed for generations despite the ever-present volcanic risk. This reality has shaped Indonesia's entire approach to disaster management. The objective is not to eliminate risk, something that is impossible, but to recognise changing hazards early enough that communities have time to respond before those hazards become disasters. Indonesia faces one of the most difficult monitoring challenges anywhere in the world. The country sits along the Pacific Ring of Fire and contains more active volcanoes than any other nation. Monitoring every volcanic system continuously requires an enormous scientific and logistical effort. Agencies responsible for volcanic observation maintain networks of seismometers that detect earthquakes beneath active volcanoes, instruments that measure ground deformation, cameras that continuously observe eruptive activity, gas monitoring equipment that tracks changes in volcanic emissions, and satellite data that provide a broader perspective on thermal anomalies, ash plumes, and structural changes. Anak Krakatau receives particular attention because of both its recent history and its location within the Sunda Strait, where volcanic activity has the potential to affect nearby coastal populations as well as major shipping routes. Modern volcano monitoring relies on the principle that no single instrument tells the entire story. Seismic stations record earthquakes occurring beneath the volcano, allowing scientists to identify changes in magma movement and rock fracturing. GPS receivers and radar satellites measure whether parts of the volcanic edifice are inflating, subsiding, or shifting over time. Thermal cameras detect changes in surface temperature that may indicate fresh lava or increased heat flow. Gas monitoring systems analyze sulfur dioxide and other volcanic gases, providing clues about magma rising toward the surface. High-resolution satellite imagery allows researchers to compare the volcano's shape over weeks, months, and years, identifying new lava flows, changes in crater geometry, or evidence that portions of the island may be becoming unstable. Individually, these observations provide only partial information. Together, they create a remarkably detailed picture of how the volcano is evolving. Collecting data, however, is only the beginning of the process. The far greater challenge lies in interpreting what those observations actually mean. Every day, volcanologists must distinguish between routine fluctuations expected from a persistently active volcano and changes significant enough to justify adjustments in hazard assessments. That task becomes particularly difficult because volcanoes rarely behave in perfectly predictable ways. A sudden increase in seismic activity may gradually fade without producing a major eruption. Conversely, relatively modest changes can occasionally precede significant events. Scientists therefore examine trends over time rather than reacting to isolated measurements, comparing current observations with historical patterns while remaining alert to combinations of signals that have previously been associated with escalating activity. Once researchers determine that volcanic conditions have changed meaningfully, the next challenge is communicating those findings to emergency management agencies and the public. Indonesia uses a structured volcanic alert system that allows officials to increase preparedness gradually as evidence of unrest grows. Raising an alert level is never done lightly because it carries real consequences for surrounding communities. Fishing activities may be restricted, tourism can decline, transportation routes may require adjustment, and residents living closest to the volcano may face temporary evacuations depending on the evolving hazard. These decisions involve balancing public safety against the significant economic and social impacts that precautionary measures inevitably create. Delaying action unnecessarily can expose people to avoidable danger, while acting too aggressively without sufficient evidence can erode public trust and create disruption that may prove unnecessary if conditions stabilize. Anak Krakatau presents an especially complex problem because many of its most dangerous hazards do not remain confined to the volcano itself. Ash clouds can interfere with aviation, reducing visibility and posing serious risks to aircraft engines. Floating pumice and volcanic debris may affect maritime navigation through one of Southeast Asia's busiest waterways. More importantly, the possibility of another flank collapse means emergency planning must extend well beyond the immediate vicinity of the island. Communities many kilometers away from the volcano itself may still face significant tsunami hazards, despite never experiencing direct impacts from the eruption. This broad geographic footprint requires coordination among volcanologists, tsunami specialists, local governments, disaster management agencies, transportation authorities, and emergency services across multiple provinces. Preparedness also depends heavily on public education. Scientific observations are valuable only if people understand how to respond when warnings are issued. Over the years, Indonesia has invested considerable effort in expanding hazard awareness through evacuation planning, community outreach, school education programs, and clearly marked evacuation routes in vulnerable coastal regions. Residents living in tsunami-prone areas are encouraged to identify the quickest route to higher ground, understand the meaning of official warning systems, and discuss emergency plans with family members before any crisis develops. These preparations may appear routine during periods of calm, but history repeatedly demonstrates that decisions made before disasters occur often determine survival once an emergency begins. Tourists present another important challenge. The Sunda Strait attracts visitors from across Indonesia and around the world, many of whom are unfamiliar with local volcanic hazards. Unlike permanent residents who may have participated in evacuation drills or hazard education programs, visitors often arrive with little understanding of the geological environment surrounding them. Hotels, tour operators, and local authorities therefore play an increasingly important role in ensuring that basic safety information is available without creating unnecessary alarm. Knowing where evacuation routes begin, recognizing official warning messages, and understanding that volcanic activity can evolve rapidly are simple pieces of information that may become critically important if conditions deteriorate unexpectedly. One of the greatest strengths of Indonesia's disaster management strategy today is that it is built upon experience gained through previous tragedies. Every major disaster has revealed weaknesses that prompted improvements in monitoring, communication, emergency coordination, and public preparedness. The 2004 Indian Ocean tsunami transformed tsunami warning capabilities across the region. The 2018 Anak Krakatau collapse highlighted the unique challenges posed by volcanic tsunamis that occur without large tectonic earthquakes. Those painful lessons have shaped new monitoring strategies and emergency planning efforts specifically designed to address hazards that were once poorly understood. While no system can eliminate every risk, each improvement increases the likelihood that future warnings will reach vulnerable communities earlier and more effectively. Despite these advances, every scientist involved in monitoring Anak Krakatau understands a fundamental truth. Technology alone cannot prevent natural disasters. Instruments can detect earthquakes, satellites can measure deformation, and computers can process enormous quantities of data. But none of these tools can stop magma from rising or gravity from acting on an unstable volcanic slope. Their purpose is not to control nature, but to provide people with the information needed to make informed decisions while there is still time to act. That distinction is essential because it reminds us that disaster mitigation ultimately depends on the partnership between scientific observation and public response. The story of Anak Krakatau, however, extends far beyond the communities surrounding the Sunda Strait. A sufficiently large eruption would not simply affect nearby villages, ferry routes, and coastal cities. It could influence international aviation, disrupt one of Asia's most strategically important shipping corridors, impact regional economies, and even alter atmospheric conditions far beyond Indonesia itself. The volcano may stand on a relatively small island, but under the right circumstances its effects could reach far beyond the horizon visible from its shores. That wider significance is where the final chapter of this story begins. When people think about volcanic disasters, they usually focus on the communities closest to the eruption. That is understandable because those populations face the greatest immediate danger. However, history shows that a major eruption can quickly become much more than a local emergency. It can disrupt international aviation, interfere with shipping, damage regional economies, and influence atmospheric conditions far beyond the volcano itself. Anak Krakatau is nowhere near the scale of the catastrophic 1883 eruption based on current observations, but its history reminds scientists that this volcanic system has the potential to affect far more than the island on which it stands. That is why governments, airlines, shipping companies, and research institutions all closely monitor every significant change in its activity. One of the first industries affected by a stronger eruption would almost certainly be aviation. Volcanic ash is far more dangerous to aircraft than ordinary weather clouds because it consists of tiny fragments of rock and volcanic glass. When these particles enter jet engines, they can melt in the extreme heat and then solidify again on critical engine components, reducing performance and potentially causing engine failure. Ash also damages cockpit windows, navigation equipment, and ventilation systems. Because of these risks, airlines routinely divert flights around volcanic ash clouds, even when that means adding hundreds of kilometers to a journey. Specialized volcanic ash advisory centers continuously analyze satellite imagery and atmospheric models to predict where ash clouds are moving, allowing pilots and airlines to avoid dangerous airspace long before passengers ever notice a problem. The Sunda Strait is equally important for global shipping. It forms part of one of Southeast Asia's busiest maritime corridors, connecting major trade routes between the Indian Ocean and the broader Asia-Pacific region. Thousands of commercial vessels pass through nearby waters every year carrying fuel, food, manufactured goods, and raw materials. While ships can usually alter course more easily than aircraft, significant eruptive activity could still create temporary exclusion zones, reduce visibility because of ash, and introduce floating volcanic debris into busy navigation channels. Even short disruptions in heavily travelled waterways can have economic consequences that extend well beyond Indonesia. Closer to the volcano, fishing communities would likely feel the effects almost immediately. Many families around the Sunda Strait depend on daily access to the sea for both income and food. Increased volcanic activity could temporarily restrict fishing areas, damage coastal infrastructure, or create unsafe conditions for boats operating near the volcano. Even if the eruption itself remained relatively moderate, these interruptions could place significant financial pressure on communities that rely on consistent access to the water. Tourism would face similar challenges. Anak Krakatau has long attracted visitors interested in Indonesia's remarkable volcanic landscape, but heightened activity often results in temporary closures, cancelled excursions, and declining visitor numbers as authorities prioritise public safety. Another question often raised is whether a future eruption could cool the global climate like the famous 1883 Krakatoa eruption. The answer is that it depends entirely on the size and nature of the eruption. The 1883 event injected enormous quantities of sulfur-rich gases high into the stratosphere, where they formed reflective aerosol particles that temporarily reduced the amount of sunlight reaching Earth's surface. Those aerosols contributed to short-term global cooling and produced spectacular sunsets observed around the world. Modern volcanologists understand this process well, but they also know that only exceptionally large explosive eruptions produce meaningful global atmospheric effects. Based on current observations, there is no evidence suggesting Anak Krakatau is approaching an eruption comparable to 1883, and it would be scientifically irresponsible to imply otherwise. Perhaps the most important lesson is that Anak Krakatau is part of a much larger interconnected system. Activity beneath one relatively small volcanic island can influence aviation, shipping, tourism, fisheries, emergency planning, and scientific collaboration across an entire region. Every ash plume, every satellite image, and every seismic signal contributes another piece to the puzzle researchers are trying to solve. The volcano's future remains uncertain, but one fact is already clear. What happens at Anak Krakatau will never affect only the volcano itself. The surrounding ocean, the nearby coastlines, and millions of people living throughout the Sunda Strait will always be part of the same geological story, which is why the coming days and weeks remain so closely watched by scientists across the world. After examining the history of Krakatoa, the birth of Anak Krakatau, the warning signs scientists monitor, the lessons of the 2018 collapse, and the broader consequences of a larger eruption, the question naturally becomes, what should people actually expect next? The most honest answer is that nobody can predict the exact path this volcano will take, but scientists can identify the developments that would increase confidence that the situation is becoming more dangerous. That distinction is important because volcanic hazards rarely change from safe to catastrophic overnight. Instead, researchers look for sustained trends across multiple datasets, watching for evidence that the entire volcanic system is beginning to behave differently rather than reacting to one dramatic ash plume or a single burst of seismic activity. Based on what is publicly known today, Anak Krakatau remains an active volcano undergoing recurring eruptive activity, which is consistent with its behaviour over much of its relatively short existence. Intermittent ash emissions, volcanic earthquakes, and thermal anomalies are expected characteristics of a persistently active volcanic system. If those observations continue at roughly their current levels without significant changes in deformation, gas output, or structural stability, The most likely scenario is that the volcano will remain active without producing a disaster on the scale of either 1883 or the 2018 tsunami. This is an important reminder that activity alone does not equal catastrophe. Many active volcanoes spend years or even decades erupting intermittently, without progressing into a much larger event. Scientists would become more concerned if several warning signs began strengthening simultaneously. A sustained increase in shallow volcanic earthquakes could indicate that fresh magma is forcing its way upward through the volcanic edifice. Significant ground deformation measured by satellite or GPS instruments could suggest that pressure is increasing beneath the volcano as magma accumulates at shallow depth. Noticeable changes in sulfur dioxide emissions might indicate that new magma is entering parts of the system that were previously relatively stable. At the same time, rapid changes in the volcano's shape, fresh fractures developing on the cone, or accelerated growth along one flank would naturally attract considerable attention because of the lessons learned from the 2018 collapse. Individually, none of these observations would confirm that a major event is imminent, but together they would represent a meaningful change in the volcano's overall behavior. One of the greatest challenges facing volcanologists is distinguishing between a volcano that is simply active and one that is entering a new phase. Nature rarely provides a clear dividing line. Some volcanoes experience months of increasing unrest before producing only a modest eruption, while others appear relatively stable until shortly before a significant event. This uncertainty is why monitoring never stops. Every new satellite pass, every seismic recording, every gas measurement, and every visual observation is compared with previous data to determine whether the overall trend is changing. Scientists are not searching for one perfect warning sign. They are looking for consistency across many different observations that all point toward the same conclusion. For people living around the Sunda Strait, the practical advice remains remarkably consistent regardless of how the volcano evolves. Staying informed through Indonesia's official monitoring agencies is far more valuable than relying on rumours circulating online. Communities in tsunami-prone areas should already know their evacuation routes, understand local warning systems, and recognise that if authorities instruct them to move to higher ground, acting immediately is always safer than waiting for visual confirmation of danger. Visitors to the region should also familiarise themselves with local emergency procedures, because volcanic hazards can develop far more quickly than many travellers expect. Preparation is most effective before an emergency begins, not after the first signs of disaster become obvious. Perhaps the most important takeaway is that Anak Krakatau is not a mystery, waiting to surprise scientists without warning. It is one of the most intensively monitored volcanoes in Indonesia, observed continuously by ground instruments, satellites, and researchers who understand both its history and its hazards. That does not mean every future event can be predicted with precision, but it does mean that any significant change is likely to be detected far earlier than would have been possible only a few decades ago. The volcano remains active, the geological forces beneath it remain unchanged, and the possibility of future hazardous activity will always exist. The challenge is not eliminating that risk, because no one can. The challenge is recognizing meaningful changes early enough that science, preparedness, and public awareness stay one step ahead of the volcano itself. That balance between uncertainty and vigilance is ultimately what defines life alongside one of the most closely watched volcanic systems on Earth, and it reminds us that while humanity has learned an extraordinary amount about Krakatau since 1883, the Earth is still writing the next chapter of its story. As we've seen throughout this documentary, the story of Anak Krakatau is not simply about one volcano, it is about a single geological system that links magma deep beneath Earth's crust, the growth of a volcanic island, the stability of its slopes, the surrounding ocean, and the millions of people who live along the shores of the Sunda Strait. Every ash plume, every volcanic earthquake, every subtle change in the shape of the island, and every new satellite image is part of the same machine that has been operating beneath Indonesia for millions of years. The eruption of 1883, the devastating tsunami of 2018, and the renewed activity being observed today are not isolated events. They are different chapters in the continuing evolution of one of the world's most closely watched volcanic systems. What is known today is relatively clear. Anak Krakatau remains an active volcano, and scientists continue to detect the normal signs of a persistently active system, including eruptive activity, seismic unrest, and ongoing volcanic emissions. Modern monitoring networks are far more advanced than they were even a decade ago. allowing researchers to observe changes in remarkable detail using satellites, seismic instruments, gas monitoring stations, thermal cameras, and continuous field observations. At the same time, there is no scientific basis for claiming that another catastrophic collapse or tsunami is inevitable simply because the volcano is active. Responsible hazard assessment depends on evidence, not assumptions, and that evidence continues to be evaluated every single day by the scientist responsible for monitoring the volcano. There are, however, important uncertainties that remain impossible to eliminate. No instrument can see directly into every part of the magma system beneath Anak Krakatau, and no scientific model can predict the exact day when an eruption will intensify or whether a future structural collapse will occur. Researchers can identify increasing risk, recognize changing patterns, and issue warnings when the balance of evidence shifts, but volcanology remains a science of probabilities rather than certainties. That uncertainty should never be mistaken for ignorance. It simply reflects the extraordinary complexity of a natural system that is constantly rebuilding itself with every eruption. For anyone living near or visiting the Sunda Strait, the most effective protection has not changed. Follow updates issued by Indonesia's official monitoring agencies, respect exclusion zones around the volcano, understand local evacuation routes if you're in tsunami-prone coastal areas, and respond immediately if emergency authorities instruct people to move to higher ground. History has repeatedly shown that preparedness saves lives, while hesitation during rapidly developing disasters can cost them. The greatest advantage modern science provides is often not perfect prediction, but valuable time, and using that time wisely is what turns monitoring into meaningful protection. Perhaps the most remarkable lesson from Anak Krakatau is that it reminds us how interconnected our planet truly is. A process beginning deep beneath Earth's surface can reshape an island, influence an ocean, disrupt international trade, alter flight paths, transform coastal communities, and become a subject of scientific collaboration across the world. The forces beneath this volcano have been at work for millions of years before the first human settlement appeared in the region, and they will continue long after our own generation has passed. We can measure them, study them, and prepare for them with greater accuracy than ever before, but we cannot stop them. In the end, Anak Krakatau stands as a powerful reminder that beneath the landscapes we often take for granted, our planet is still alive, still changing, and still writing its history one eruption at a time. At